Now let's first prove that T prime is a tree. How do we construct T prime once again? We took the tree T and we added in this edge E star. That created a cycle. Now along that cycle, we removed any edge of that cycle. In this case, we removed, let's say, this edge. Let's call it E prime. What we're going to show now is that we can remove any edge of this cycle, and this resulting graph T prime will be a tree. Now how are we going to show that T prime is a tree? Well, we're going to show that T prime is connected and it has exactly n-1 edges. Now if you recall from the beginning of the lecture, we said that if a subgraph has exactly n-1 edges and is connected, then it must be a tree. Now the fact that it has exactly n-1 edges is obvious. Why? Because T is a tree, so it has exactly n-1 edges. We added one edge in and removed one edge, so we still have exactly n-1 edges. So what remains? We just have to show that it's connected. So take any pair of vertices, y and z, and let's show that there's a path between y and z in this subgraph T prime. I chose a particular y and z in this example. So y is over here and z is over here. Now notice in T there's a path between y and z, of course, because T is connected. The path goes along this edge E prime. Now what happens in T prime? Well, in T prime I've removed this edge E prime. So this old path between y and z no longer exists in T prime. So let's let P denote the path from y to z in T, in the original tree T. And now we have to construct a path in T prime which goes from y to z. Now recall that when we looked at T union E star, what do we get? We got a cycle. These blue edges are this cycle in T union E star. So let's let C denote the cycle in T union E star. Let's denote the endpoints of E prime as C and D. Now E prime is a path from C to D in T. Now this cycle C has two paths between C and D. E prime is one of those paths. Let's take the other path. So let's look at this cycle C and take out the edge E prime. What do we have? We have a path. And this path goes from C to D, and all these edges in this path exist in T prime, because T prime contains all these edges except for E prime. But we're not using E prime. We took E prime out. So we took the cycle, dropped off the edge E prime, and this gives us a path from C to D in T prime. So how do we get from Y to Z in T prime? Well, we're going to follow the original path P. But whenever we hit this edge E prime, we replace this edge E prime by this new path P prime. Now, to show that Y and Z are connected in T prime, so we want to show that there's a path from Y to Z in T prime. Well, we're going to use the original path in T, and then whenever we hit the edge E prime, we're going to replace the edge E prime by this path P prime. Because the edge E prime does not exist in T prime, but the path P prime does exist. So we're going to go along this path, and now the original path uses this edge E prime, but it doesn't exist now. So we use the rest of the cycle. That gets us over to D, and then from D we follow the rest of the path P. So actually in this example we're backtracking. So this doesn't actually give us a path, it gives us a walk. But it shows that that Y and Z are connected in T prime. And then of course we can truncate this walk to make a path. But our whole point is to show that Y and Z are connected, and that's all we need to show. We've shown that's the case for any Y and Z, therefore T prime is connected. And since it has exactly n-1 edges, then T prime is in fact a tree.